We are broadcasting and I am saying things. So here we go. Hello everybody, welcome to this week's ExoLife Hangout. My name is Tony Darnell. I run deepastronomy.com and soon to be deepastronomy.space, and I cannot tell you how excited I am this week for this week's Hangouts. You know, these Hangouts are just getting more and more fun. I'm getting so excited about each one. Today's topic, we're going to be talking about something that it wasn't first noticed by Enrico Fermi, but I think he was the first that got famous for saying it, I suppose, where we're going to be talking about this idea that the galaxy is old enough and there are enough stars in it that there has been plenty of time for a civilization to have developed and colonized a substantial part of the galaxy, or at least to the point where we might notice it. And he posited the question, well, if that's true, then where is everybody? We should have seen them. And we're going to talk about this problem a little bit because it's actually a very deep, I think, and subtle question on so many levels. And I am very grateful to have an old colleague join me who's written a paper that I have absolutely not been stopping to think about since I first ran across it back in my days at the University of Illinois. And I also have in my hangout a biologist. I'm going to introduce you both of them in just a moment, as well as my normal co-host, Dr. Jeff Kuhn. But before I do, I just want to remind everybody that we are broadcasting on YouTube, which I'm looking at the live chat now, and I'm hoping you guys will answer some questions, or ask some questions. Don't answer them, because that's what I think we're supposed to do, or at least talk about them. And I'll read them out as we go along. Also on Facebook and as well as Twitch. So I hope you guys are, if you're watching on any of those, please keep your comments and questions on those platforms, and I'll hopefully find them for you and read them out to our guests. So, also, real quick, I just want to announce that if a lot of people have been asking, well, how do I find out about these Hangouts and which ones are coming up? You can go to deepastronomy.com/hangouts, and you will see a calendar there, which will, you can see all of the events that we've gotten confirmed with guests and things like that, as well as all of that kind of stuff. Now, for this Hangout, I've got some reading material for you. If you look in the description box of the Hangout that you're watching right now, you'll see 3 links. You'll see a link to Dr. Jim Annis's paper that he wrote on AstroPH. I have a link to that. I also have a link to a paper written by Dr. Nick Bostrom, who is a Swedish philosopher who written a good treatise on why it would be a bad thing if we found life on Mars. And there's also a link in there to a web page also discussing the Great Filter by Robin Hanson. So you want to follow along on either of those, you feel free to do it and ask questions as we go along. Okay, my guess. First up, I'm going to go from right to left, and get rid of that lower third, because that's not you. First up is an old colleague friend of mine, Dr. Jim Annis. He works at Fermilab. Hi, Jim. You are an astronomer, right?
By training.
And you work at a particle physics accelerator, so that's interesting, and that's the topic of a Hangout all on its own. But I want to welcome you. Thanks for joining us on our Hangout. Also joining me is Dr. Peter Ward. Let me pull you. I've got so many buttons to push here. Here he is. And let me get you lower third up. There you go. Dr. Peter Ward, you're in the biology department. You're a professor in the biology department at University of Washington, correct?
Yes, correct. But I was originally trained as a geologist, so I kind of do double duty.
Oh, wow. So you're like, so geology, biology. And now you study evolutionary biology too, right?
Yes, that's correct.
Excellent. Okay, good, because I'm going to make good use of that in this Hangout. And, of course, joining me as he does each week also is Dr. Jeff Kuhn from the University of Hawaii. He is also a member of the Planets Foundation, of which I meant to point out that these Hangouts are a collaboration between the Planets Foundation and deepastronomy.com. And Dr. Jeff Kuhn is a member of the Planets Foundation. So, hi, Jeff.
Good morning, afternoon,
You were threatening me before the Hangout, It was a little bit scary.
Oh no!
Yeah, we got a lot to talk about. That's why you said it. Like you're gonna.
This is going to be a long hangout. Yeah. I think this is going to be at least.
Yeah,
this is like page 1 of many chapters. Right?
That's right. Okay. Well, let's get started. We got so much to talk about. We live in a galaxy that I want to set the stage. First of all, folks, I want to talk about we're going to talk about the backdrop of how life exists in our galaxy by talking about the galaxy itself. And to do that, I want to get Jim, if you and Jeff also, you feel free to chime in as well. Give us some intro into the galaxy itself, as well as how many stars are in it, how big is it, and things like that. Just sort of set the stage for us. Jim?
Well, so our galaxy is something like 100 billion stars, and it's something like 30,000 light years from us to the galactic center. 24,000, I think, is the accepted value. You get to double that, 50,000 light years if you want. 100 billion, 10 billion stars, and a lot of stars. They're not all sun-like. They go from M dwarfs, which will be faint and dim, to very, very bright things like Rigel, which you can see all the way across the galaxy. But the bulk of the stars are probably medium-class stars, like the Sun and F stars, and I can do this, K stars.
And so, and in addition to just having these stars, however, though, the brand new, we've been talking about this in these Hangouts a lot, brand new study of exoplanets. A lot of planets out there too, right?
So, when we were last talking, last time, there weren't a lot of exoplanets. And I remember the days when it was thought that planets were rare. But somewhere around 2000, we started finding exoplanets all over the place. Ignoring that planet found around a pulsar in around 92. There are planets everywhere we look. They're scandalously mini planets. It's fabulous. It's a whole field of astronomy, which I know very little about.
Yeah, and a lot of these now, and a good portion of these planets they're rocky planets. I think the most common type planet that is being found, and Jeff, please chime in if you've got something to add to this, are Neptune-sized planets, but a non-trivial amount of these planets are rocky and in this thing they call a habitable zone. Is that right, Jeff?
Yeah, so as Jim's number is tens of billions of stars. I think the thing to remember is that what we now know that we didn't know 20 years ago is that there are more planets than there are stars out there. So when you look up at the sky, you can only see the stars with your eyes, but there are more planets lurking around those stars than there are the stars themselves. And the other number we should probably expose is the age of the Milky Way, which is something like 13 billion years old. So it's old, it's big, it's heavy, it's large, and it's got lots of planets.
Yeah, and so there is a lot of possibility here for life to be here in our galaxy. The ground is fertile, as I'm liking to say it. It looks like there's problems on the YouTube stream. Is that right, Kevin?
Yeah, I think so. It's buffering a lot right now, so we're just trying to send everyone over.
Okay, but it's looking good on Twitch TV. So, and also don't forget Facebook too, guys. We're on Facebook.com/Deep Astronomy, and it should be on that as well. And I'm looking at the comments on that as well. So go there if YouTube is having a problem. Okay, so that's the galaxy. It's big, it's old, it's got lots of stuff in it, and a lot of these planets they could harbor life. We hear about it all the time with TRAPPIST-1 and Proxima b could be in a habitable zone. So all of these things, liquid water, all kinds of fun stuff happens. But these are just the stage. This is just the stage for life and where it could form within our galaxy. Now let's talk about Earth. We know Earth has life on it. Maybe not intelligent life. I'm kidding. We know that Earth has life on it because we're here. We look up. And when we look up at the sky, we're listening hard. Just last week, we had people on this Hangout telling us how hard they were listening using the Allen Telescope Array, and they still haven't heard anything yet. And I want to get down to why that might be. But before I do, let's talk about life on Earth. Life on Earth is let me get Peter involved in it. Peter, are you there? There you are.
I am indeed. Can you hear me?
I can hear you and see you. Go ahead. So I want you to let's start first of all, Peter, with how do you guys define life? To a biologist, what is life?
Yeah, it used to be a pretty simple definition, and interestingly, that's one of the oldest scientific questions of all. I mean, what is life? And we put in life metabolizes, so it's taking energy from outside itself. It's compartmentalized. I mean, you can't have you go to Star Trek, you can find every kind of life you could ever imagine. But you can't have life in a solid because chemical reactions reactions don't work fast enough, or in a gas, there just aren't enough atoms to hit one another. So the compartment, have it metabolize, have it be able to replicate. And finally, the very cool one is it must be able to evolve. And Carl Sagan added that in. Life has to have Darwinian evolution as one of the definitions. But here's where you hit the rocky shoals. Is a virus alive? And I personally think yes, but when you get to this whole virus definition, when it's in a spore form or it's outside its host, I mean, that's deader than dead. So when you get to simpler life, these definitions, which seem so discrete and easy, aren't. And really, there's another one. We talk about life and death as binary. I mean, death is like a continuum. So there is alive, all right, but you can have things that are totally dead and then come back to life. And so this is what is, I mean, dead, or dead, or really good and dead. So this
dead
is
a
another
continuum?
new area.
Did you just say that?
Absolutely. And my colleague Mark Roth, who
I'm
is
thinking of
working
Princess
on
Bride now and like mostly dead.
Or zombies. Keep going.
So for astrobiology, you know, there's a whole lot of life up in the upper atmosphere. And that stuff is being hit by cosmic rays and solar radiation and all this stuff. But it's even bacteria are in this really, they're in their own little spacesuits. But if you took one of those and said, is this alive? No, there's absolutely no idea that metabolism is taking place. They're not replicating. They're not doing anything. They're dead. But they come back to Earth and they're alive. It's alive.
Oh, okay. Well, so so you said that it has to, I'm glad you brought up Carl Sagan, because he also seemed to think that life is a pretty straightforward thing on Earth, that once you give it the conditions for life, then boom, it's pretty much a certainty. Do you agree with that?
Lots of caveats. Why is it, even from Darwin, who thought about small ponds, science can still not say where life first formed. And it's almost like building a 747 or a 777. It appears that life's constituents may have actually formed in totally different environments and then have been brought together in an assembly area. But the fact that we just have made so little progress that there's still this big argument about hydrothermal vents. Perhaps it was on mineral surfaces within vents, but then others say that you've got to have intertidal, you've got to have water coming and going. I mean, it's still up in the air.
Okay, yes or no question. This is it. The whole hangout hangs on this. Is life going from stuff that isn't alive, that's dead, regardless of the continuum, and you've got all the right building blocks, you got all the stuff you need for life to be there, but it's not alive, to being alive, is that step easy or hard?
Well, that's impossible to say. But here's evidence to the contrary, that it may be harder to get than we think.
I mean,
one of the excuses, one of the reasons people keep going on is that they say life formed on Earth almost as soon as it could have. But this isn't true at all. The best evidence for early life is the Isua carbon isotopes. And there's been more work on this recently. Isua is 3.8 to 3.7 billion years, but the Earth is 4.567 billion years of age. So that's a pretty good stretch. But even now, we've got the first fossil life that we find is about 3.5 to 3.4 billion years. So can you say something's easy that takes a billion years to form?
yeah.
So there you are.
Yes, I can.
But wait a minute. Yeah, wait. We didn't have an ocean. We didn't have any of the conditions that we thought we needed to get autocatalytic molecules at work. I want to step back just for a minute, because Tony's question really begs the question of what is life, and so the biologist definition, I think, is what you gave us, Peter. But Schrodinger had a different definition. We had a panel at the last EPSICon meeting a few weeks ago. We put 5 people up on the panel, and we asked exactly that question: what is life? And can you imagine the diversity of answers we got? So from a physicist, we got the answer that any system which is sufficiently far away from equilibrium could be considered lifelike, because we could imagine that those systems could also go through some sort of complicated evolutionary. So a hurricane, right? Hurricane is in this definition life.
A hurricane.
Well, it's a system which is so life is peculiar in that it metabolizes, but it exists outside of the equilibrium. We say we are peculiar, and we're surrounded by room temperature. Or in Hawaii, we're surrounded by really nice temperatures, but our bodies exist outside of that. And the processes that make life work are processes that are extremely rare and different and far from equilibrium. And
Jeff, could you bring up the concept of negative entropy, which I thought was always classic from Schrodinger?
Well, I think that Schrodinger, a lot of his ideas, I think, at least we also talked about his view of life in this 2-hour session one evening. And so entropy is this idea that everything evolves towards a greater amount of disorder. And of course, when we look around and we build buildings out of random rocks and we look at the surface of the Earth compared to a random disordered system, we'd say, well, there's less disorder in what life does than what there was before. So it looks like entropy is going in the wrong direction. Now, the truth is that that's a statistical statement. And at the molecular level, there are reactions that are very non-entropic. They create locally an environment which has less disorder at the expense of the environment around them, which ends up having more disorder. But I just wanted to get back to this idea that,
but Jeff, you can't
and I think you
communicate
said
with disorder. We want things that we can communicate with, that we can build a civilization around, right? That's
right.
what we're, that's what would be to me the
right. So the question that Peter raises is, did life take a long time to get started? Is a fundamental question, and it depends on your definition of life. That's my point. It's just
okay. So we really, I guess the point here is we don't really have a good working definition for what that is.
Well, if we go in the year 2017 to a major meeting of thousands of biologists and
you get
astronomers
6 different answers,
and the main question in some public debate is what is life, then there's something wrong with what we're doing.
Okay.
Or maybe not. Maybe it's just a sign of a young, vibrant, as you can tell from this discussion, set of questions that are ripe for further thought. But I just wanted to inject the notion that the definition of life.
Okay. So I didn't expect that we would maybe define it here in this hangout, although I was hopeful. But we'll go ahead and leave that. But I think we're going to use sort of a common sense sort of building block kind of thing, our analog for life in the discussion going forward, which brings me to Fermi's paradox. So we've set the stage. We've talked about the galaxy, lots of stars, lots of planets. Life is, once it starts, at least on Earth, it's pretty darn able to go just about anywhere it wants to. We don't know if it's easy or hard. We'll come back to that. That might be a filter, right? But we'll come back to that in a minute. But let's talk about Fermi's paradox. And Jim, I wonder, can you summarize for us what that is? What is Fermi's paradox? What is the question that he asked?
What I think Fermi did in the back of his head, he was famous for these calculations you could do on an envelope. And you'd get factors of 2 wrong, but the answer would come out right. The Fermi calculation. I think what he did was he just took Earth orbital velocity and asked how long it would take at orbital velocity to go from one side of the galaxy to the other. And that's 100 million years. And that sounds like
orbital velocity of the Earth.
Or going around the Earth, Sputnik.
Okay.
It's all about the same number. It
100
just doesn't
million
take,
years.
It just doesn't take that long to go across the galaxy. I mean, for individual human life, yeah, of course, but even a species lifetime, that's long. But 100 billion years on cosmic timescales just is not a long time. The galaxy rotates 200 million years, so if anything starts moving in a straight line, you get spread out pretty fast, covers most of the galaxy. If you have a universe that's 13.5 billion years old, and maybe even put aside some amount of that before stars form and galaxies form, but you get the first planet, and if life forms fast, then you get an early life form, an early civilization. You follow the thread of logic through to spaceships. And then as soon as they get spaceships, as soon as they get any mechanism at all of travel between stars, they should have covered the entire galaxy. All of it, many times over, in the span of 1 billion years, 2 billion years, 3 billion years. There's been lots of opportunities for life to have done that. That is remarkable. Even in the context of the conversation we've had here, it took in round or numbers 5 billion years. The Earth's been around for about 5 billion years.
Right.
It took 1 billion years for life to form. You still have 4 billion years. Now, how long will it take us to go all the way across the galaxy? I don't know, but odds are it's tomorrow on cosmic timescales.
And you mentioned in your paper that the relevant timescale that we care about is that it took less than 1 billion years for life to form, but the timescale is the important one. At least in your paper, you said it was for the rise of intelligent life, right? That's what we're concerned about, and that timescale is even shorter.
It sure seems like it. Most of the 4 billion years that life has been around has been not much of anything. Less than 1 billion years of things we'd recognize as animals. Of that, up until, let's say, 60 million years ago, it was dinosaurs. Up to 100,000 years ago, there were intelligent hominids. In the last 100,000 years, we've done everything. Cities, spacecraft, internet.
And so and that is in once, so like we talked about, once you get there, once that time scale is compared to the lifetime of the galaxy and lifetime of stars, things like that, that's not very long. And so let's say we got to a civilization starts colonizing, and you say that as soon as they reach some kind of spacefaring ability, then they should be everywhere, more or less. And there's basically, let's talk very briefly about the ways in which people might colonize the galaxy. As I see it, there are two main ways. One way might be you could launch a spaceship, travel out there to it, the regular conventional way, colonize it, and maybe terraform it, things like that. That's one way. Another way is to build these self-replicating probes that can do it these are unmanned and can do it in much less time. And Jeff, I would love it if you want to comment on this too, but that length of time is not very long. I think the information I have here is our galaxy is about 100,000 light years across. If a probe were capable of traveling at 1/10 the speed of light, every planet in the galaxy could thus be colonized within a couple million years using these self-replicating probes. And if it were set to 1% the speed of light, colonization might take 20 million years instead. So either way, we're talking a relatively short amount of time to colonize the galaxy, compared again to the age of the galaxy itself. Any more comments on that? Not going to take very long, would it? Now,
how about this is the thing the science fiction people never want to hear. What if it is impossible for biological beings to go even to the closest stars? What if we do, you get intelligence rising and then they never can get out?
There's these science fiction ideas that sound wonderful, like you take light sails and you move them up to 1/10 of the speed of light, and you send them to Proxima Centauri. But instead of leaving cameras there, you bring in cloning equipment. You don't send biological species, you send a recipe for biology.
Right.
Yeah,
clearly science fiction.
But it's actually not a bad idea. And so some of the debate around this breakthrough starshot program is, well, okay, so miniaturizing a PCR machine or a DNA printer is something that's in fact a little bit easier than building the 150 gigawatt laser that we need, to be frank. And so I don't think that's off the wall at all. I mean, here's another question, right? So do you think that simpler life forms on Earth know that we exist, like ants or E. coli? Or so when we say we haven't had any contact, well, we're at this phase where evolution is now transferring information from one generation to the next, not really by genetics, but by digital information. There's much more information transferred. And so evolution has completely changed. Survivability now has to do with our computers and other modes of educating the next generation. So we're completely, you might say, screwing up evolution, but in fact, maybe this is a natural step. And in 40 years from now, instead of being attached to the internet with my cell phone, I might just choose to have a USB 15 and be able to upload everything that's in my brain into something which is not biological. So when we talk about did we have contact, I think that's wrapped up to this question of whether or not we believe that we're only going to be talking about life as we know it. And when we ask, well, did we have contact? It's not obvious, I think, that we haven't had contact, because I think answering the question of some sufficiently advanced species that were to visit us and thinking of ourselves as bacteria compared to what we're looking at, that might not be an easy answer.
Okay, are you saying, Jeff, that we may have been in contact with another civilization, we just don't know it yet?
I would even go. Let's be even more provocative. What's the best self-replicating probe you can think of? It's life, right? Build a little coded message into a 10⁵ base pair prokaryote, put it on a Starship probe, and squirt it out into space. I mean, this von Däniken had this idea, but he had a slightly different
I haven't heard that name in years. Okay, well, all right, well, okay, but then wait for it to evolve into a civilization, right?
Right. If all you got to do is build something that mutates, wants to survive, metabolizes.
Okay, Jeff. So even then, it goes up to it's a numbers game, right? It's sooner or later there's going to be a civilization out there that maybe is going to talk our language, at least something that we can understand. You used ants. Do ants even know we're around? I would say, yeah, they know we're around, especially when we step on them. But they're self-aware. Maybe they don't know what hit them, but they know something did. And if we're an ant, if that's your analogy, and something else is talking to us that we can't recognize.
But suppose we're within. I mean, if you listen to the singularity hype, right? In 42 years, well, but the only true exponential in human civilization is the growth of the communicable information that we record, and that is doubling every 3 years, and you go back to the printing press to see that curve.
Yes, but you're a physicist. It doesn't ever keep going.
I know. Thank you. That's exactly right.
That one is going on, and that's not the point. The point is that we are going to reach this phase where the amount of information which is in my brain is more easily manipulated and contained in something else, which is not carbon-based. And so, well, maybe it's carbon-based, but it's not going to be me, or it's not going to evolve through the wet chemistry that we call biology. I just think that we're missing something when we don't allow for the possibility that it may be that we're within 100 years of a complete change in what evolution is and what life is. And if that's true, then who knows?
Okay,
who knows what
maybe
what
we are, but certainly somebody else would have reached that long ago. And if they had done that, the question is, why aren't we hearing about it? You're saying one possibility is that we can't, that maybe they are, and we just don't know how to listen because it's just different. It's too different from us. We wouldn't recognize it if we saw it.
Here's an analogy. Why do you plant grass around your house?
It's very pretty.
It's pretty. It keeps the weeds out, right?
And
so suppose the self-replicating probes happened with a civilization that evolved and went through this transition to non-wet chemistry evolution 4 billion years ago. And they said, let's plant grass so that we're not overrun with a species which is not as benign as we are and is a threat. So we'll squirt a bunch of nanoprobes out into the universe, put 10⁵ base pair self-replicators on them, and we'll fill the universe with grass. We're the grass. If we're the grass, I don't go out of my house and communicate with my yard that way.
But it took less than 1 billion years for grass to turn into humans, and on that time scale. So I'm convinced. Even if you did that, you would get, in my mind, a lot of exploration through evolution to find forms that work in local environments. And apparently that can include intelligent life. If you think that happens often on lots of planets, then you have this situation where you have lots and lots of evolutionary trials, which probably include intelligent life. And you get this situation where you're assuming that all of them transition to some kind of system that does not wish to propagate through the galaxy as themselves, or don't wish to affect their environment at all.
Well,
It only takes one that loves changing the environment they live in and moves through the galaxy to leave behind all kinds of evidence that you can just see.
I can't nod my head big enough. That's right.
Well,
absolutely.
But wait. So if we had populated the universe, or someone had populated the universe with nanoprobes, then all of us would be at about, in this corner of the universe, would be at about the same level of development. And so who knows what's going to happen? If we go
Well, the question is why it took so long for that to happen. For me, I mean, it's just too long.
Why? Why is
It's been too long since you probably could have gotten life in the universe.
I don't know why that is. I get at 10 billion years or 3 billion years or 1 billion years. They're all numbers that we don't really understand and we can't really predict.
I know, but we do have a base mark. We do have a baseline of at least one instance of generally how long this stuff takes. And that's us. And it's not an unreasonable, while we don't occupy any special place in the universe, there's nothing that says we, are special and can do things quicker. It's pretty easy, I think, to then say, well, this is not an unrealistic way to look at how other things might have come up on other planets. So I want to get to the Great Filter. We haven't heard anything from anybody yet. Jeff says just wait. Who knows? We're not done yet. There's still plenty of time, and there may not. And I think you're arguing there may not even be one. But let me first start by defining what a great filter could be, and then we'll all talk about that in just a minute. And I'm going to use a definition that I read from Nick Bostrom, who's a Swedish philosopher who wrote. He does a lot of studies on living in simulations and existential sort of writings, things like that. And I really liked his definition, so I'll just start here. The Great Filter can be thought of as a probability barrier. It consists of one or more highly improbable evolutionary transitions or steps whose occurrence is required in order for an Earth-like planet to produce an intelligent civilization of a type that would be visible to us with our current observation technology. In other words, you start with billions and billions of potential germination points for life, and you end up with a grand sum total of 0 extraterrestrial civilizations that we can observe.
Yeah, well, that's silly.
I happen to agree, but okay.
You agree?
Yeah.
Why is that silly?
Why do I think it's silly? Because I think...
And then also tell me what you think the Great Filter definition should be.
Let's see. The way he phrased it, it's you start with life, and somewhere along the process between life and a galaxy-wide civilization, an internal event happens which turns it all off.
No, he does not start with life. The creation of life itself could be a highly improbable event. That it could also be a great filter. And I want to go from this definition to some possible candidates for great filters. And one of them is that maybe that step from going from 0 life to life is a filter. That may be extremely difficult. So he doesn't assume that. He just
Tony, can I demonstrate why I think that he's missed something important?
You may. Go right ahead, Jeff.
I have a deck of cards here.
Oh, good.
All right. If you were next to me, I would come to you with this deck of cards and I would fan them out for you, and I would ask you to pick a card. Okay, and let's say you pick jacks. And then what I would do is I would shuffle the deck, and then you would take the top 3 cards from the deck and they would all be jacks. Now, why is that relevant? Well, so it's relevant because the chances of that happening are infinitesimal. And we look at and we apply the physics that we understand, and we would conclude that, well, this I couldn't do it again, but I would do it again, and I would do it again. And each time you would pick a card, and I would shuffle the deck, and those cards would appear at the top. Now, of course, that's magic, right? It's magic. We understand something at the level of the physics of how a shuffle works and the statistics and the probability, which is how we look at this problem. But what we miss, right? What we miss is an understanding of there are other ways of explaining how to do this, and that's exactly what a magician does. And the truth is that biology, in several stages, has done magic at a level that automatically, I think, Nick Bostrom and maybe Peter, you would say, well, it's so unlikely. How could it happen? How did it happen that RNA evolved and we had autocatalytic reactions that could make proteins? And then how did it happen we could make DNA and we could encode from one generation to the next? And then how did we go from simple organisms that were prokaryote to eukaryote cells? And then how did we get to multicellular life? And it goes on and on. There are a whole bunch of miracles that happen.
No, stop using those words.
And it's not magic.
You're using magic and miracles, and that's not...
I can show you a magic trick, and it's not a miracle. It's just you didn't understand what I did and the sleight of hand that's part of magic.
Highly improbable events do not mean impossible events. And these are, you could, in fact, get that scenario with the deck of cards if you had enough stars in the galaxy to make this happen. So okay, neither one of you like that definition. So tell me what you might think a good definition, and please, Peter, chime in as well. Do you have any ideas for what you think a great filter might look like?
Well, it just occurred to me when I heard about that we're the grass, I was starting to think, what's the lawnmower? And maybe it is these gamma ray bursts, or just mowing all the lawns down.
I'm really hurrying.
Really mowing them down.
Doesn't quite work, but yes.
All right. So go ahead, Jim.
So I think even the first time I heard this from Robin, I thought the phrasing was just not right.
I agree. The phrasing is weird. I couldn't agree more about the phrasing. But the idea isn't.
It's the base thing is that it appears it doesn't take that long for life to form. It doesn't take all that long on cosmological timescales for intelligent life to form. And it doesn't take any time at all to colonize a galaxy once you get intelligent life. And so the question is, why don't you see them? It's really the great science. Why don't you hear them? Why don't you see them? Why isn't the galaxy teeming with life? And then Robin Hansen postulates a great filter because you don't see it.
Right. And that's the step you have a problem with.
But how do you know
there are other ways?
The problem is he makes an assumption, which is we don't see life, and that is an assumption.
Well, yes, but you don't. I mean, that's
yeah, it's kind of true, Jeff. I mean,
because Earth-like life on another planet we couldn't see. You simply would not be able to see it.
No, but let's imagine, my classic is that a galaxy-wide civilization has swept through this part of the galaxy, and it did it 100 million years ago. So if it wasn't mean to sweep through, well, there's questions. If it's really probes, that's one thing. If it's entities, if it's beings, that's another. If it's beings, they would probably build shopping malls on old dead places like Mars or the Moon, which have these 4 billion-year-old surfaces on them, and we've looked at them. They look really natural.
Okay,
so you haven't looked every square meter for a probe. I mean, I give you that. We haven't looked for hidden cities in the outer Kuiper belt. I give you that. But everywhere we look, everything just looks natural. There's not a whole lot of places where you can point to and say that just doesn't look like something that would happen in nature.
So let
me ask a rhetorical question here to you physicists. How far away from the Earth could you still see all the lights on the dark side? And all these mercury vapor lights and all the electric lights and all the energy we pop out at night. Could you see that from Alpha Centauri? If you were just
you could not.
So it would you couldn't pass that far away.
But
what about a
that's
spectrograph?
No, that doesn't help. The largest signal that you might look for is not the lights, but the thermal signature of civilization. So life has a thermal footprint, and civilization has an even brighter thermal footprint, the heat print of cities. And we are within 10 years of being able to build a telescope that on the nearest planet, which is Proxima Centauri b, being able to see that. But that's my point. If we're looking for life which looks like us, we can't We can't see it. Now you say, well, it should have advanced. It should be more advanced. But my point there is, if it is advanced, it's not going to look like us. It's going to be incredibly different because we're in this sort of exponentiating world. And you could say, well, all right, so it's possible that life about our stage kills itself out. Maybe that's true. But then why is it that we appeared 13 billion years into the life of the galaxy, and what happened for the first? I mean, I think my analogy with the magic trick is that nature is doing magic, but it's not, because we just don't understand the sleight of hand that makes life. We can say, well, it's terribly unlikely, but there are miracles of life on this planet that have occurred that don't have anything to do with our existence. The life that exists in hydrothermal vents, the life that exists in freezing cold environments. Those are miraculous things, and they took place. And you might say, oh, they're so unlikely. How could they possibly have existed? But they didn't have anything to do with our existence. They're not in the chain of command that leads to humanity. So my answer to this is, first off, we don't know that life hasn't passed through here. We may very well be the evidence of that life. And life is so robust and so miraculous and so non-understood to us that the existence of other branches to the living tree on the earth, I think, is ample evidence that it isn't so impossibly rare to make something that looks like humans. Okay.
I need to get to the part where I talk about Jim's paper, because I really want to do that. And
Great.
I want to just, for the sake of a discussion, let's go with this idea, Jeff, that if we have not heard from anyone yet that implies the existence, doesn't guarantee, but implies that perhaps there is this idea of a filter that prevents life from getting to the point where it can colonize the galaxy and make ourselves known. And Jim, please give us a summary of your paper that you wrote a while back explaining one possible way that might prevent a civilization from getting there. You make an incredibly good argument. I'd like to hear it.
So the idea has to do with the way to defeat Fermi's question is to make the time scale super short. So what you have essentially is a 10 billion year lifespan for intelligent life to arise and run over the galaxy. And that's a problem. There's so many time scales in that 10 billion years. So shorten that 10 billion years down to as short as possible. If you can bring it down to about 4 billion years, then that seems to be a time scale for the rise of intelligent life. If you can bring it down to that kind of time scale, then you don't have Fermi's paradox. How do you do that? Well, you don't do it internally, because planets form at all times during the life of the universe after the stars form. So you do it externally. Externally could be something related to star formation. One thing we know that's happening in the universe is these gamma ray bursts. Gamma ray bursts are thought to be predominantly, the most energetic ones, magnetic stars that are collapsing down to neutron stars or onto black holes, which shoot out these jets. These jets are very, very luminous in gamma rays. They're very luminous, period. Those gamma ray jets, those beamed particle beams, which include gamma rays, are incredibly bright. And if you're in the beam path, they could, in principle, sterilize planets. If they were numerous enough in the early universe to stop intelligent life from forming, if they happened, every star in the galaxy got beamed by a gamma ray burst every billion years, that would probably stop intelligent life from getting a foothold. So that sort of works. The star formation history of the universe is very highly peaked around redshift 2, and it falls pretty rapidly from there to now. So the rate of gamma ray bursts is much higher in the past, that's actually observable, than it is now. That kind of works. There are lots of caveats around that having to do with, we're not talking about life, it's more like intelligent life. Life under the ocean certainly would not be affected by muon beams hitting the top of the atmosphere, hitting the ground.
Okay, so is it? So if I understand what you're saying, right, this is more like some kind of EMP that would affect the technology of a civilization more than it might affect the radiation might affect the life itself. Is that right?
No, it kills the people. It kills the entities. Muons are lethal in sufficient doses.
Okay.
So if you're in space in a spacecraft, you're probably dead. Maybe they're shielded. If you're on ground, you could be dead, depending how close you are. If you're under a couple 100 meters of water, you probably live. If you live under the ground, you probably live. But surfaces of the Earth are not that well protected from particle beams.
So these are mass extinction events you're talking about.
But what about the dark hemisphere? So the other side of the planet, of course, is shielded by the planet. So regardless of where it comes from, don't you have something that survives? I mean,
Well, you have the ocean vents. You always have the ocean vents.
Yeah,
So
you
it's
always
not
have the
just-
oceans, but then you got the dark side, the unexposed side of the
If
planet.
it lasts for a second, or if it doesn't last for a long period of time, we know the flashes don't from gamma ray bursts. We don't quite know about the particle beams. Yeah, there are issues with this. So in the paper I wrote a zillion years ago, it was pointed out that this mechanism, gamma ray bursts, as the reason for galactic-wide sterilization events is not terribly great. You have to work out the details of it. And people have been doing that over the last decade or two. The current thinking is it still doesn't quite work. It worked up to about 5 billion years ago, and maybe it doesn't work after that.
Because they don't happen as often, is that right?
Yeah,
Okay.
and the rates aren't high enough to actually, you have to be in the beam to be damaged. This question is how wide the beam is, and what covering fraction you get hit by. But in fact, no, I can't go that direction. You go back this direction. But the idea is, if there's
Go that way.
if there's some kind of way of killing off most land-based life in a galaxy, be that be supernovae or gamma ray bursts or something we don't quite know yet, then you could reset the timescales and you wouldn't have the Fermi problem.
But don't the asteroids do that for us already? I mean, asteroid major impacts and the major extinction events, right? Those are already happening on tens to 100 million year intervals. I mean, the gamma ray burst is great, but I think we already have this issue of mass extinctions.
We have several mechanisms for mass extinctions that don't have much to do with the supervolcanoes, asteroids, and these explosions that happen. The thing you have to do is somehow kill off all terrestrial life forms. And this is a sort of a posit that you can't build spaceships if you have to lift water into the orbit.
Yeah.
So if all you need to do is kill off terrestrial life forms and not all life, then that's a plausible thing.
Okay. So this, because I know people are thinking it, and I thought it when I read your paper. On Earth, we know our stellar neighborhood pretty well. Are there any places in the sky that are particularly threatening to us with this event? And if so, is there any way to predict when it might happen?
No, so we're sort of past that.
So we're really not. We're really. So you would argue if this is a filter, then we're past it.
If this is a filter, so the way I phrased it in the paper was a phase transition from a time when essentially intelligent life is suppressed by these events. It just made it very unlikely for intelligent life to actually arise until the gamma ray burst event or other galactic extinction events became rare enough that you started getting life to come up, intelligent life to form. And that event must have happened somewhere in the last 5 billion years, that phase transition or the cessation of the filter.
Okay.
Why? Because Earth life. It doesn't necessarily make Earth special. It just makes it one of the first things to come out after the cessation of galactic-wide killer events.
Did you want to add something to that, Jeff, or was that just...
No, I think that this extinction events is something that we have to figure out, right? Because the asteroid, the dinosaur event was 60 million years ago. Yeah,
the only one I thought was plausible was a Permian extinction. It wasn't even the recent ones. It was one of the earliest ones that wasn't.
Yeah, 93% of species were extincted.
Yeah.
The problem, right, is once life gets a foothold, it's like killing cockroaches. It's just
I couldn't agree more. But the question I want to get to is this idea of a civilization. I think you're absolutely right. It is definitely true that life is like that.
So I made this point in that paper that dinosaurs had a long time to form intelligent life. They never did.
That's true. They were around a very long time. So,
And like evolution is trying out. It has body plans and it tries out various things with them. But maybe some body plans work better than others for intelligent life.
yeah, the problem with evolution is it's not very efficient, right, Peter? Maybe you can comment on this. It sort of tries everything, and whatever works, right? Is that a good way to look at that?
Yeah, and actually we're going through a pretty cool new revolution in evolution. We're going back to Lamarck. Neo-Lamarckism is suggesting that you can produce evolutionary change 1,000 times faster. And the reason we think we're getting these huge outpourings of new types of body plans and species after the mass extinctions is the environment becomes so wrecked that it allows us transition from random Darwinian evolution, which is really slow, to this crazy, really rapid change through methylation. You're turning genes on, turning them off, you're exploring all kinds of stuff. I mean, one of the coolest things, if you look at what happens when you domesticate a wild animal, the first thing that happens, if that animal no longer has to worry about my getting food or being eaten, you get this multiplicity of form. Look at the domestic chicken. I mean, the domestic chicken is now touted as the most rapid evolutionary change in a vertebrate. We go from, Gallo is this little forest creature that looks like a miniature chicken. But boy, we've produced the Long Island Reds and the pullets and all that stuff. Dogs too. You just domesticate and boom, off they go. The other possibility about the filter is life itself. I've argued, I call it the Medea hypothesis, that life is always self-defeating and that, in fact, the only way out is the rise of intelligence. But, I mean, it just remains to be seen. One of the equations, how long do civilizations last? And we know that even all the way back to Sagan and the famous equation that civilizations may be inherently self-destructive to a higher extent than we want them to be.
And that was also that brings me to a point where that might also be one of the examples of a filter. It could be that when your civilizations just don't make it past a certain point in their technological evolution for a variety of societal or technological reasons, things they just get eaten by their own technology in a lot of ways. And that's one candidate also for a great filter. So there's lots of reasons for why there may not be one, and of course, as Jeff is fond of pointing out, and I agree with him to a certain extent, we don't know what we don't know yet. It's fine. There may be plenty of time yet for civilizations to contact us. We may already have been, and we just don't know it. But I want to explore this particular idea of the great filter, and now I'd like to ask you guys, and this is a vital question, do you think it's ahead of us or it's behind us? Now, if it is one of the things that Jim's talking about, which is the gamma ray burst, he says chances are that we've escaped it. It probably isn't going to affect us. Other civilizations that have come before probably didn't. So we got lucky there. But what worries me, and I'd like to get you guys' comments on this, is if we find life in our own solar system, let's say we go to Mars and we find evidence that there was life there that was actually started there. It didn't come from Earth and jump over there, but it was actually indigenous to Mars. That would suggest that life, that step we were talking about earlier, going from zero life to life, is actually not as hard as we think because it happened twice in one solar system. What are your thoughts on that? Anybody?
How are you?
Well, one of the hardest things. Oh, go ahead.
Sorry, no, go ahead.
Yeah, I tell my students if we get to Mars and there's three possibilities. We know we can build DNA in many different ways. I mean, it doesn't have to be exactly as we've done it. People have put together. This could be different language, different coding, even different amino acids. But if we get to Mars and we find that life is exactly like our DNA life, oh my gosh, I mean, it could be from Mars to Earth and Earth to Mars. If it's a totally different DNA, that's the best really possibility. It really does look like separate creation. But then there's the third possibility, there's no life on Mars at all. It's just the tough one is, if it may be that, in fact, you can build lots of different kinds of DNA, but in the long run, only DNA like ours is the test of time. It always has to be like our DNA. So you can have a separate creation of our kind of DNA. It's just a parallel evolution, and we would never know.
So I would have added that I think that if we found the same DNA on Mars, it doesn't prove that it has any relationship to the Earth. It may be that's the lowest state.
Yeah, exactly. That's the point.
And it could have come independently, just like it came on Earth, or it could have come via comets. I think it's worth mentioning to those that don't know, right, that the mean spacing of comets is interstellar distances, and so the notion of panspermia that goes back a long ways is not by any means dead, and so natural probes that propagate life are almost as efficient as this idea of sending nanocraft with biological markers. So I think it's going to be really hard to deduce that life on Mars was really a separate strand, unless, as you say, it has a different DNA alphabet. And it's interesting to point out that we have synthesized, right, X, AGC, and X recently over the last few months as an artificial coding. But
I would go for Enceladus as my point of looking for life that's different.
Yeah. Go ahead. Enceladus? Yeah, that's an exciting place.
Well, because it's covered by ice, so life that formed in the bottom almost certainly didn't come from Earth via a rock transfer, nor did it come from probably comets.
That's an excellent point. So yeah,
there's a shield around it.
But either way, Peter, please give me your thoughts on this. Wouldn't that point to the support of the idea that starting life isn't so hard? If we find it in two spots here in the solar system and discover that they weren't related, like panspermia, that's a pretty bad sign as far as the filter still being ahead of us, correct? Would you agree with that?
And I've always thought really one of the first people off that Mars lander ought to be a paleontologist with a coring device and look for microfossils. But I like the Enceladus, but I like Titan more. If you really want to find life as we don't know it, most of our solar system is really cold, and you can certainly get other types of. We use water, of course, but a solvent such as ammonia, there can be the possibilities of cold life. You can use silanes as the structural building blocks of these things. Plus that big, thick atmosphere, you've got a beautiful way of parachuting in, if you will, or even using gliders getting down there. It's technically much easier to look for life on Titan than it would be on the Jovian moons, trying to get through that damned ice.
Interesting. And you're right. That is, if we wanted to find life as we don't know it, that'd be a good place. What do you think of that, Jeff?
Yeah, but I remember the extremophils that live here on the Earth. We've got life that lives under freezing conditions. We've got life that lives in temperatures above 100 degrees C. Knowing the environment is not, and knowing how extreme it isn't proof that it doesn't necessarily have the same origin. But yeah, okay, Titan in a methane kind of creature with a very different DNA, I think in that case it would have to would be compelling that life happens perhaps not so difficultly.
Okay, well, I'm looking at a lot of the chats here that we've had going on, and I'm sorry about the problems with YouTube, guys, but I'm glad that you guys were able to. It looks like they got over to Twitch and Facebook, all right, Kevin?
Yeah, exactly. Most people moved over to Twitch, so we're doing all right.
Okay, good. And I'm seeing the chat there. It's going pretty crazy. Howard Kuhlman is commenting, civilization only took us 3 million years from being monkeys, not long. Only 200,000 years from bashing rocks together. Blink of an eye. How do we know that this us evolving hasn't happened on Earth before? It only takes 100,000 years to wipe out all evidence of us. Is that true, Peter? It only takes 100,000 years to wipe out. If we suddenly died 100,000 years from now, we would never know we were here?
Well, clamshells can last hundreds of millions of years, and a freeway is made of the same stuff as a clamshell. So, I mean, if we had a technological civilization, I'm pretty sure that there would be evidence of it. So I've never really ascribed to that aspect. I mean, there's a really interesting new movement called the Anthropocene to make it a geological unit. And people are trying to say we could use Earth garbage as the marker of that. But you can't really. I mean, we geologists have really hardcore rules. And I propose, this is a little off topic, but what would be the one fossil that could show up from our time right now that would suggest that we have become this civilized creature? And the best vertebrate fossils are teeth. And whenever you find teeth in your 5 million years from now paleontologist that's got amalgam fillings that's had dental work, you know damn well we're right at the start of the Anthropocene, right as it is. I mean, we're burying people and we're making fossil humans like crazy right now. There's going to be a whole lot of us out there with these drilled skulls. Practical moment.
All right. Well, I guess gosh, damn, it's already 8 o'clock. Okay. Well, I guess we'll have to stop there. I've just so much. We didn't even get to a lot of the stuff I wanted to talk about as far as evolution goes. But
Jeff, we warned you.
Yeah, I know. Yeah. It was only an hour. It's all we had. But what do you? So, just some final thoughts from each of you on this idea of the great filter. I know. Give me your thoughts. First of all, do you think there is one, and do you think we're ahead of it or behind? And I'll start with you, Jeff. Go ahead.
I believe in an optimistic universe of infinite possibility, OUIP, and I think that given that assumption, I am not troubled by the Fermi paradox.
So there is no paradox as far as you're concerned.
Well, maybe it's a paradox. I just don't understand it.
Okay.
I'm not troubled by it.
Okay. Jim, how about you? You got any comments?
I'm pretty sure the Fermi paradox is a problem, and I'm pretty sure that the answer is something like gamma ray bursts that make it so intelligent life can't live even up to 5 billion years ago.
So you don't think it's a civilization issue, a technology issue? You think it's an astrophysical one?
Absolutely, and I think the implications of that are, like in your language, the filter is behind us. It's never been a filter about us. The universe has been inhospitable to intelligent life until lately. The corollary of that is that if you take that seriously, then all over the galaxy, there are civilizations waking up and looking around, just like us. And 100 million years from now, the galaxy will be full of life.
So, wait a minute. So, because of the timing of the fact that the gamma ray bursts are mostly behind us, because of the evolutionary state our galaxy is in right now, we're gonna civilizations all over the galaxy are waking up right about now
and start inventing. Yes, they shouldn't be all staggered. They'll be staggered in time on human time scales. But not on cosmic time scales. On 1,000,000-year time scales, they're just popping up.
I love that thought. So the universe or the galaxy is just starting to wake up, perhaps. I like that. How about you, Peter? What do you any thoughts on this great filter business? Is it all bunk? Do you believe it exists at all, or?
I think it's a great idea, but I'm still hung up on rare earth and thinking about, as a geologist again, tectonics. Look at poor Venus. Venus, just because of a different tectonic regime and just the way it reduces heat, there's no way there's life on Venus unless its extremophiles are more extreme. So, I mean, like the TRAPPIST system where people are saying, oh, yeah, look, we've got these Earth-like planets. That phrase is so overused.
I know.
None of those planets are Earth-like. It's just, and the super-Earths, right? A super-Earth-like. No, I mean, you really have to have some way of a thermostat to keep a planet at a reasonable temperature for long periods of time. You can't do it without plate tectonics as we know it, if you're going to have billions of years of constant temperature.
Well, that sounds like a hangout right there. I love to talk about that with the context of the exoplanets, TRAPPIST, and these close ones we always hear about. So, all right. Well, thank you guys. I want to thank my guests very much for taking time out to be with us. I'm going to have to cut it off there so that I want to make sure I respect their time. I want to thank my guest, Dr. Jim Annis from Fermilab, as well as Dr. Peter. What's your last name? I got to write it down.
Ward.
Thank you. Sorry, I wrote it down and I moved my papers. Dr. Peter Ward from the University of Washington Biology Department. Thank you both for taking time out for joining us. Jeff, you're fun as always. I love being in Hangouts with you, so thank you for joining as well.
Bye, guys.
Next week, I think we're going to be talking about, and Peter, I'm just going to invite you now if you want to come back next week. We're going to be talking about
this is fun.
The frequency of life. Is life common? and we're going to talk about that question alone next week. That's the frequency of life is what we're calling it. So that'll be next week's Exoplanet Hangout. And we also, if you want to learn more about what hangouts are coming up, go to deepastronomy.com/hangouts and look at the calendar there, and I will try to fill them in as quickly as we get guests confirmed. So on behalf of Dr. Jim Annis and Dr. Peter Ward, and Dr. Jeff Kuhn, thank you all very much for watching, and as always, keep looking up.